Okay, ladies and gentlemen, esteemed guests and passionate advocates for our ocean and our planet, I wish you a warm welcome to this Ocean Pavilion event titled Plankton and Climate Change, Indicators, Stressors, and Carbon Storage, and thank you for joining us bright and early this morning. My name is Sarah Davidson, and I am the Dr. Biliana Season Fellow at the Global Ocean Forum, a position created to focus on ocean climate initiatives, and in particular, foster international and intersectoral discussion to break down silos and promote ocean and climate action. Today, we will be delving into the intricate web of connections between our changing climate and the tiny but mighty organisms that inhabit our oceans, which I hope will prove to be an enlightening and crucial gathering focused on the intersection of climate change and the often overlooked yet vital world of plankton. Plankton are the base of the ocean food web and mediate our climate. Plankton communities are susceptible to climate change, with implications for ocean carbon storage and fisheries. Today, we will discuss indicators of change in plankton communities and indicators of change in plankton ecosystems from sustained observations, new technologies that will help us understand these changes better, potential tipping points in plankton ecosystems, and potential early warning systems, and the implications of these changes. As we gather in this space dedicated to ocean and climate awareness, we recognize the pressing need to address these challenges posed by climate change and the pivotal role that plankton play in this global narrative. From the microscopic wonders of the ocean to the far-reaching impacts on our climate, our discussions today will work to unravel the symbiotic relationship between these tiny organisms and the health of our planet. So before getting started, I would like to welcome briefly the speakers who will be joining us today. Dr. Cael, who is the principal scientist from the Ocean Biogeosciences Group at the National Oceanography Center, will start us off with a presentation on plankton, climate, and their interactions. Then, Lynne Talley, a physical oceanographer from the University of California, San Diego, Scripps Institution of Oceanography, will present on sustained ocean observations for ecosystem change. We will then hear from Ken Buesseler, who is a senior scientist at Woods Hole Oceanographic Institution, who will present on how the ocean can help solve our climate crisis. We will then hear from Hans-Otto Pörtner, head of the section Integrated Ecophysiology at the Alfred Wegener Institute, who will present a holistic view of blue carbon and explore challenges and opportunities to mitigate the climate and biodiversity crises. Finally, we will hear from Grace Cawley, a PhD student from the University of California, San Diego, Scripps Institution of Oceanography, who will share with us about the connection between zooplankton and the fisheries and as bioindicators for climate change. We will then end with a Q&A session and closing remarks. Thank you for being a part of this vital conversation. I will now pass it off to Dr. Cael.
Thanks, Sarah. So hey everybody, I'm Cael. I just wanted to sort of start us off with a brief overview of plankton, why plankton care about climate, vice versa, and so why we should care too. If I can get my slides to change. So there we go. All right, so just to start off, what are plankton? So plankton are basically, or phytoplankton, are basically the trees, shrubs, and grasses, all of the plants of the sea. And then zooplankton, which we'll hear a little bit about later, are the herbivores. And just like trees on land, plankton come in all kinds of different shapes and sizes, and also provide all kinds of different sorts of ecosystem services, which are indispensable for the Earth system. So this is a schematic of the flows of carbon through the Earth, and this is sort of the context in which many of the plankton ecosystem services take place. And one thing that you'll notice is that even though plankton, which are the sort of microbes box here, comprise 1/100th the size of the reservoir of carbon on Earth that the land plants do, they're responsible for the same amount of photosynthesis as all of the land plants on Earth. So even though they're tiny, they're mighty in the sense that half of all the photosynthesis on Earth is due to plankton. And furthermore, the amount of carbon that is moved by this process from the upper ocean into the ocean interior each year is the same amount as the carbon that humans put into the atmosphere. And so this is a sort of critical natural way that the Earth system has to remove carbon from the atmosphere for long times. So this in particular is responsible for about 10 gigatons of CO2 of carbon sequestered for 100 years every year. So from a marine carbon dioxide removal perspective, plankton are way out ahead in front of us. They have had about a few billion years head start, so it's okay, we're just catching up now. But also, when we think about the amount of carbon that is stored in this way, climate models tend to predict that it's going to decrease with continued global warming, but also these predictions between different models vary a lot, which underscores the need to better understand this very vital process in the carbon cycle. The other flip side of this is that plankton also are affected by climate change. So for example, because it's never too early in the day for a bit of shameless self-promotion, this is from a recent paper where we analyzed 20 years of data from a satellite that measures the color of the ocean. And the reason that we care about the color is because the color is determined by the plankton communities that are in the water, which means that a change in the color necessarily reflects a change in the ecosystem. And we were able to show that anywhere that this map is purple, that the color of the ocean, and hence the plankton ecosystem, has changed over the last 20 years. And while we don't yet know what specific ecological changes these color changes correspond to, we were able to show with climate change simulations in a climate model that these color changes may indeed be due to climate change. And so that indicates that climate change is affecting plankton communities over so much of the ocean here. We think this is probably happening because as climate change continues, it becomes more difficult, especially at low latitudes, for nutrients from the deep ocean to get into the sort of sunny waters where plankton grow in the surface, but this is sort of work in progress. The same model actually predicts that we'll see much more abrupt changes in future with continued climate change in plankton ecosystems. So wherever this map is colored, these are different properties of the ecosystem that have a kind of tipping point in them, which really underscores the need for these sort of sustained observing programs that Lynne will talk about next. So this is an example of 30 years of data from a time series in Hawaii. And we really need to continue these kinds of programs so that we can, over time, detect these climatic changes and distinguish the changes that we observe between anthropogenically caused ones and natural variations. And so with that, I'll close and I'll pass back to Sarah, leaving up a few take-home messages. Thank you.
Thank you, Dr. Cael. Your introduction to how plankton and the climate interact was a wonderful way to open this session. I think that your comments on the importance of observing plankton ecosystems as a vital aspect for both assessing and understanding climate change was particularly salient. And I can't help but agree that plankton are tiny but mighty, and I also can't help but agree that it's never too early for a bit of self-promotion. So thank you so much for sharing your wonderful, very interesting, and cutting-edge research. I'd now like to welcome Lynne to speak.
Hi. Those of you that know me know that I'm not a plankton person, so I am a physical oceanographer, but I've also been very much involved in building observing systems, and I'd like to talk about some of them that I think can be critical for tracking ecosystem change. So there we are, the transition. There are out there in the global ocean a set of observing systems, including the station Aloha that we've already seen. This is an illustration of what we do with ships. We traverse the ocean and we make measurements. I'll show a slide of what we're doing. And we can drop floats that go in. There are satellites from above that are all looking down. And important for this topic today is that all of these are making measurements that are relevant to the ecosystem of the ocean. So I'm going to talk about profiling floats, use of research ships, and then some fixed location sample, for instance, like in Hawaii and OOI. And then I won't really talk about satellite measurements, but that wonderful result that Cael showed of his own. We picked it out ourselves without knowing it for our presentation yesterday. So, so observations. This is part of a traditional oceanography. It's global shipboard observations, coast to coast, top to bottom, reference standard measurements that are repeated every 5 to 10 years. And this has been really critical for tracking the heat content changes in the deep ocean and for tracking carbon storage in the ocean and changes in the carbon cycle. There's an emerging program that goes with this Ghost Ship program, which is called Ghost Ship. And they've successfully gone to sea on Ghost Ship for the last few years, separately funded, looking specifically at plankton communities. And they have a website there. The second type of measurement that's really, I think, essential at the core of tracking change is a growing biogeochemical autonomous network. These are profiling floats. And then if you're familiar with profiling floats that do temperature and salinity, they've been doing that for 20 years, down to 2,000 meters for temperature and salinity. We've been building a network over the last 10 years that also measure biogeochemical variables, and they also measure fluorescence backscatter and are starting to measure downwelling irradiance. So those are interesting to you all. Here's an example of a time series station. This is at Hawaii, and just showing what's going on with carbon. This is a stressor on the system. This is not measuring the up and down, the breathing, the seasonality on there is the plankton. What you see at the top is the really well-known Keeling curve. In red, it says atmosphere. That's Mauna Loa. That's the carbon dioxide record since 1989. And you see it rising. And you see a little bit of a seasonal cycle on it, and that's the ocean breathing. Under that, you can see the same length of time series at the Hawaii Ocean time series, and that is just north of Honolulu. And they have measured PCO2 in the surface ocean. You can see that going up, usually a little bit lower. That tells you the direction of the flux. And then down at the bottom, you see the pH. At the same time that the carbon goes into the ocean, that also acidifies the ocean. So one of the things that is important to keep in mind that is while the ocean performs a really important service in taking up 25 to 30% of the carbon, that also changes the acidity of the ocean. So that is something, this is an example of an amazing time series that has been continued and continued into the future, hopefully not to end. This is a sort of an emerging map of acidification from our biogeochemical floats. At the beginning of our array, we started in the Southern Ocean. We wanted to understand the carbon cycle and look at the primary productivity and the biological pump throughout the Southern Ocean to improve models there. And it is the hardest place in the Earth's surface to really monitor. Ships don't go there in winter. So over 10 years, we have collected enough data to show that the surface ocean down there, all the blue is where it's become more acidic over the last 10 years compared with historical data from about 20 or 30 years before that. So you see it's everywhere, and that's scary to me. I was seeing that map for the first time. You also see some spatial pattern in it, and that begins very mushy because we don't have a lot of floats. We're using model statistics to map, but you do see a more intense acidification towards the coast, and that is something that's been predicted. You can also measure, though, important with these floats is you can measure down into the inside of the ocean. And so we can see how the pH changes with depth. And it's not the same as at the surface. And we hypothesize, and we're quite certain, I think, that that's due to the circulation, the overturning circulation of the ocean. This is an example just straight off of Ocean Data View of what we can do with our Southern Ocean floats for chlorophyll and particulate organic carbon, which is from the fluorescence and the backscatter sensors. You see a nice pattern, but it's sort of eyes glaze over. What you're seeing here is time on the x-axis. So over the last 10 years, and then on the y-axis is latitude. So you're starting in the south near Antarctica, going north across the Antarctic Circumpolar Current and up into the subtropics. So if you look at the chlorophyll, this is in the upper 20 meters of the ocean. You can see a very nice seasonal cycle, annual cycle. Down towards the Antarctica, it's really, really easy to pick out: red, blue, red, blue, red, blue. And then you can see how what its change with latitude is. You can also see where our floats started coming in as we were building the array. In the bottom plot, you see the particulate organic carbon that's going at the same time in the upper 20 meters. Emphasize that we're measuring all the way down actually to 2,000 meters, 1,500 meters to 2,000 meters. You're not going to find much chlorophyll down there, but you can slice and dice this. You can start to see interannual variability in this record. We're not seeing a trend yet. It's not long enough. It's 10 years. And the interannual variability we would hypothesize is southern annular mode. And this is an example from Johnson and Biff using the biogeochemical Argo data to calculate net primary production from the changes in oxygen. There are different ways to do this from the floats. At the top, you see a map of chlorophyll in May. And so that's basically showing you, what it looks like. In the slides at the bottom, you see on the left the daily cycle from floats in the northern hemisphere. You can see it going up and down with the daytime. And in the middle is the seasonal cycle. You can see the seasonality in the oxygen production. That blue dot matches in time that map at the top. And on the right is looking at that as a function of depth, which we can do with the floats. So that basically ends what I'm talking about. This is a final map that Johnson and Biff published, looking at the latitudinal distribution of that productivity based on biogeochemical Argo float oxygen. So this is related directly to the plankton that are out there. The blue curve is what's from the floats, and behind it are from the satellite estimates. So that's what I have to say. We basically, what we're selling here is the importance of sustained observations and what you can do if you've got a float array out there that's sampling every 10 days in areas that are totally inaccessible by ships. And so you're getting a picture down into the ocean that matches what you're measuring with the satellites. So thank you.
Thanks, Lynn. Your speaking points did a really excellent job of further stressing the importance of observing the ocean, particularly how you noted on your opening slide that we cannot manage what we do not observe, which I thought paralleled very well with this bigger theme of plankton, since I think that the role of plankton is often poorly understood or just not very popularly promoted in the ocean community. So I thought that was an excellent parallel. I'll look forward to tracking the research and results that come from that BioGo ship expedition that you mentioned and the work that will come from their observation of plankton communities. And as you emphasized right at the end, it can take decades for research to show trends which can be translated into policy. So it is very crucial that that research is not only prioritized, but supported and continued. So thank you again, and now let's hear from Ken.
Thank you for that. Let's see. Oop, am I going the wrong way? Not enough coffee yet. We're going to switch directions a little bit, but it is still a story about the mighty and tiny plankton, because we're going to talk about the climate crisis and why a lot of us are here at COP. Basically, I want to just introduce what I think is a bit an optimistic story when you think about the climate crisis, the human suffering, the environmental losses, but we know what we have to do. And it's really two things. That gray line there is going down. That's the emission reduction curve, what you're seeing as CO2 emitted by humans every year. And we've got to bring that down. We know how to do that. We've got to get to decarbonize our electricity and power sources. So that's in the plans. How well we do will be a product of meetings like this and what our society decides to do. But we've also when you look at those types of curves and you try and keep the temperature to something like a couple degrees, maybe it'll get a little bit higher, we have to include that blue part below the line, which are negative emissions carbon dioxide removal. There's already CO2 in the atmosphere that has to be removed, and we'll always have residual sources. So those two things we have to do. I think we know how to do them. Now, the other thing I'll point out here is just the scale. We're at near 40 billion tons a year being emitted. We've got to get rid of about 5 or 10, so keep those in mind as I move ahead and talk about gigatons, billions of tons of carbon dioxide or carbon. So we need CDR, we need carbon dioxide removal. So we're here in Ocean Pavilion. Why are we talking about the ocean? And it's really not just because often these talks get introduced that cover 2/3 of the Earth and the oceans there. Well, for carbon, it's a much bigger role. It's much bigger than that. And if you look at carbon, where it ends up, that number in billions of tons in the atmosphere is around 600. If you look in the ocean, the storage in the interior is 37,000 billion tons. So that's 50 times more than the atmospheric reservoirs. The one that, when I started showing this first, surprised me is if you add up all of the land plants, all of the soil carbon, you get to 2,500. It's about 15 times more in the ocean than all of those land plants. So that's very important, and how we perturb those really will matter then to the CO2 in the atmosphere. So I was fortunate in 2020 to be asked to be part of this committee, which I said no to at the academies. I said, we got to get on with experiments, but I said, let's review, if we look at ways you could perturb the ocean to take up more carbon dioxide, how could we do that? So we were tasked to look at 6 of these. On the left are more what we call the natural solutions, nature-based. On the right, the engineered, and this is where plankton are going to come in, right? Plants, through photosynthesis, take up carbon dioxide. I think this audience knows that, so you can grow the macroalgae, things like seaweed plants, and you can do things, and I can talk mostly about iron fertilization, the phytoplankton, enhance their growth by adding in an iron. Those are 2 ways that use plants. The ocean tube model you might not have heard as much about, but you can bring up deep waters, which have higher nutrients. It's a slightly smaller circle because you're bringing up some of the dissolved inorganic carbon too, so it's not easy because you have to get that back down and more. You can have ecosystem recovery 30 by 30, the idea of the ocean interior, the enhancing basically biomass. It's a slightly smaller circle because you can get to maybe millions of tons, hundreds of millions of tons. If we doubled ocean biomass, we can't get to billions of tons per year. But it's an important thing to do, and you probably should be doing it. But it's not a big dial. You can scale things up that are engineered, like alkalinity, ocean alkalinity addition, enhancement. On the right, basically grinding up rocks, putting them in the ocean. It just takes a lot of ground up material to do that, but you can scale that essentially to enhance the solubility pump so that it takes up more of that CO2. And you can change solubility by electrochemical. Factories essentially takes a lot of energy, but you can change the ocean chemistry with electric currents being put in the ocean. I'm going to talk now for the last few moments here about one of my favorites, ocean iron fertilization. I've had a pretty long career studying the biological carbon pump, including experiments back in the 90s and early 2000s, where we would go out and go to these areas that are limited in their growth. We know plants need nitrogen, phosphorus, the right temperatures, but they also need small amounts of iron. And if you go to places like the Southern Ocean that we were focused on, say the last talk, it's an ice-covered area, so there's not a lot of dust, there's not a lot of exposure of ways to get iron in the ocean. And so those are the types of areas where, if you go experimentally, John Martin was the hero in this early in these days, and add in iron off the back of a ship, we can do things like, these little jars, you start to create more of the chlorophyll. This was particularly true for the diatoms, so those tiny, mighty diatoms, that's a Chaetoceros, they're not from that experiment, but they're the ones who respond the quickest and grow quite rapidly. And we were pretty impressed with ourselves when we could see these events from space. That's a satellite image at 60 South, the Soiree experiment, I believe. But the other number there that's useful to keep in mind is it doesn't take very much iron. So 1 ton of iron gave us 2,000 tons of carbon removal. There's been a lot in the press about direct air capture in Iceland and how successful that is. That was 1,000 tons of CO2 removal. This is 8,000 tons of carbon dioxide equivalent. So in 1 month, we got a pretty substantial response. Now, Mother Nature that number is like 1 to 50 to 100,000. So we can, one of the challenges is how can we make that number bigger? But that's not carbon sequestration. This is growth. We made things green. We proved that iron was a limiting nutrient. What we're setting out to in newer experiments, we hope that we can start, is what is the fate of that carbon? Can we get durable additional carbon removal through the biological pump? So you put iron at the top, you have the biological response, and you get this flow of carbon through primarily sinking particles in terms of the deeper sequestration. If we can get it down, usually it's about 500 to 1,000 meters. It depends on where you are in the ocean. You can have a durability on the order of centuries or even deeper in certain places, millennia. It's not permanent. There's only about 1% of that carbon that actually gets buried. But for our climate crisis, if we can be storing carbon for another 100 years, several hundred years, that will make a big difference on that climate dial. And as you saw in some of the numbers that Cael showed us, that pump at the top is 10 billion tons leaving the surface. So enhancing that, we could certainly get to the gigaton scale in certain parts of the ocean when you put it all together. So how would you do this? I mean, there's a commercial pathway. That's what's happening in most of these methods where venture capitalists are buying credits. We decided, we got back together, some of the people I was working with, and formed this group exploring ocean iron solutions. I put exploring in caps because we don't have a solution, right? We're just trying to do the studies to figure out things like durability, the scaling, can we really get to that billion-ton mark? What would that do to the ocean? What are those ecological impacts by greening certain parts of the ocean? What are the costs? And then I'll end on some of the ethical issues. So we've gone a long way. There's about 25 institutions. We have monthly forums. We have over 50 scientists who have been talking about this for about a year and a half. And this QR code, I've got some copies of it I can hand out, gets you to a new document only a month ago that looks at the scale of the experiments, the type of models we'd need, the type of technology to monitor, report, and verify that, some of the social and governance issues that go along with that, and just basically, I call it the bake-off. What's the best form of iron to put in to get the highest response? That 1 to 1,000, can we get 1 to 10,000? That would make deployment certainly much easier. So I'll end on here because kind of how we do our science really matters. And I think this is quite important too, as we compare CDR done, say, through academics versus some of the commercial ventures, where they're not necessarily trying to have certain intellectual property that they retain so they could make a big profit. 1 billion tons times $100 per ton is a pretty big market. So we set out in the first months. Margaret Lynne is one of our participants at Scripps, and she had a conference about 15 years ago looking at the ethical ways to move forward with CDR. We turned these into 5 bullets on prioritizing this for the benefit of humans and the environment. We shouldn't be doing this otherwise. Can we have clear lines of responsibility? Who's in charge, basically? We need to have open research. That's something academics do already. We need to perform these in iterative ways, allow anyone to come in independently. If we go out in the field, this group Exodus, you're welcome to join us. You can bring your ships out, do your studies. We're going to need that. Markets will demand that if there's a cost to carbon. And we certainly want to be at earlier stages, bringing the public in for the need for CDR, and why essentially, in my mind, all of these should be moved forward. I just happen to work on the iron one. So we can talk about others later, but I think this is an important thing to end on. Thank you.
Ken, thank you. Your optimistic and I'll say very functional approach about knowing what needs to be done was quite a refreshing take, I think. However, the scale of the climate issue can still feel overwhelming. And yet, I think you did a wonderful job today of showcasing also the sheer scale of the ocean carbon capacity and describing how plankton and nature-based solutions can play a role. I could not agree more that science needs to lead the way when conceptualizing and mobilizing ocean climate solutions. And so your mention of also the just add iron work is a great example of how sometimes there are simple solutions which can act as starting points for informing further solutions for our complex climate problems and turning that climate dial, as you mentioned. So thank you also. I just want to end on thanking you for putting mention of ethical considerations as you're pursuing these ocean climate solutions, because that is so important. So thank you for that, and I'll now pass it off to Hans.
No. Yeah, thanks a lot. And I'm going to add to this story a little bit. Thanks a lot for being here this early and for the opportunity. I'm joining this discussion as former co-chair of IPCC working in Group 2, where we have emphasized ocean issues in the sixth assessment cycle, producing, for example, the Ocean and Cryosphere report in 2019, and including ocean findings also in our main assessment report. And certainly in that kind of context, developing a holistic picture is important, and putting the current situation with respect to the capacity of the ocean to store organic carbon into that picture. We recently then in the European Marine Board produced this policy brief that talks about blue carbon and trying to analyze the situation in whether blue carbon is well defined as it is currently used in the literature, whether there could be some progress, and to what extent actually blue carbon connects the climate and the biodiversity crises. So the traditional definition of blue carbon was focusing on carbon that can be managed, and certainly then the focus was on coastal vegetated ecosystems with rooted vegetation, mangroves, tidal marshes, and seagrasses. But the findings that were increasingly reported in the literature and here in this context, phytoplankton as well, it makes it necessary to really connect these elements and to see what the ocean is actually doing anyway, and what it might be able to do if it is manipulated, as we've just heard. So it needs to include the coastal shelf and offshore marine sediments, where we at the moment have large carbon stores that should not be perturbed and should not be mobilized and mineralized, and CO2 being brought to the surface. And this brings the attention to some elements of the carbon cycle that haven't traditionally been included, elements of the biological carbon pump that are involved in bringing carbon to the bottom of the sea into the marine sediments. So the animal side has traditionally not been valued as being very important, and I think that picture is changing, and it's interesting to see that it is also changing with respect to green carbon, because rewilding is increasingly being discussed as a mechanism to increase carbon storage in soils, and as an indicator how in the future ecosystems could be managed to increase carbon storage. So kelp and macroalgae, they absorb CO2 but do not bury it, and calcifying organisms should also be considered, but the dilemma with them is they can certainly trap and store carbon in the sediments, but during the process of calcification, they emit CO2, so they're not, it's not a straightforward approach. So we have widened the definition of blue carbon in this policy brief to cover coastal vegetated ecosystems with rooted vegetation, plus marine coastal continental shelf and offshore sediments, and that connects nicely to what we've heard about the role of the phytoplankton. And certainly the most important issue is the long-term storage of carbon, considering that blue carbon organisms are vulnerable to climate change. So that leads and connects to the question to what extent this can actually be a climate solution, or whether keeping the capacity of solution can only happen under the precondition that we ambitiously cut emissions, and that seems to be the case. So with this schematic picture of the biological carbon pump, I just want to add to the previous talks, re-emphasizing that the carbon that is being bound and the organic carbon that is being formed is along its way down deep. Most of it, it's remineralized, and only a very small fraction is really reaching the deep sea. And as Ken has been describing, there have been attempts over the year. Our institute was also involved in some of these studies to increase the carbon that is being exported down deep, and use ocean gyres and ocean currents to actually help that process. There are constraints on the capacity for blue carbon, and one of the constraints, if it comes to coastal systems, certainly is a spatial constraint, where you have areas where, okay, current ecosystems are being destroyed, and where you can say we need to restore those, and some of this is underway. In other places, destruction is continuing. Then the suitability of substrate, the human use of coastal environment is important. And although there seems to be a role for them, the roles of whales and fish needs to be quantified, because that kind of order of magnitude, how they actually accelerate carbon export, is a question. So there is a high uncertainty around carbon accounting, and there is a need for reliable monitoring in the open ocean and also in the coastal areas, and in order to demonstrate the benefits for climate policy actions. So what policymakers are currently doing, kind of referring to that, the nature-based solutions as a solution to climate change, is certainly a shortcut that is not at all justified. So with this final slide, I'm kind of summarizing the insight from this according to the dimension of and the capacity of the natural systems and the remineralization processes involved, which actually involve also the oxygen stores. So the fate of the oxygen, whatever we do to the ocean, the fate of the oxygen is important. And the current picture is that it's only a small, less than 2% contribution to mitigation, less than 2% of current emission rates. So it's not a solution to, at least not a short-term solution to the current climate crisis, but its long-term contribution to climate stabilization can be significant. After emissions have been strongly reduced, and that is like the time scale of these processes is something that needs to be considered in the political discussions much more than it has or is currently being done. We need more research in order to develop recommendations for funders and policymakers, and there is certainly uncertainty about the amount of carbon removed and stored, because it has to be stored as organic carbon that usually, preferably happens in oxygen-poor environments, and that is important to consider. But there may be a downside to this, because there is a possible production of methane and nitrous oxide involved that is then counteracting the blue carbon story in a way. So we need to emphasize the co-benefits as we go along, and certainly not just emphasize the carbon side. The protection and conservation of blue carbon ecosystems will contribute to solving both the biodiversity and climate change crisis, because if we restore natural ecosystems and their ecosystem functioning, it's really stabilizing and increasing the resilience of biodiversity in those systems, and it keeps the capacity intact to help us in the long term with climate mitigation under the precondition that we are able to cut emissions and keep global warming best to 1.5 or close to 1.5, because in a way 1.5 is kind of flying out of the window currently. And it's essential to emphasize this and not allow anybody to use blue carbon as an excuse to keep emissions going. Thank you very much.
Well, thank you, Hans, for your holistic presentation on that policy brief about blue carbon, which you noted highlights uncertainties and challenges, but also provides key recommendations. And I have to say that this is why I think it is so important for researchers such as yourselves to be present at the COP to address uncertainties and challenges head on, while also hopefully increasing understanding, thus increasing support for ocean and climate initiatives. Particularly, I thought that learning about the expanded definition of blue carbon, which you highlighted today, I think that will be a crucial step forward towards understanding long-term opportunities for climate stabilization. And I appreciated your nod to green carbon as well, as I think it is important to keep a pulse on the terrestrial world, just to make sure that we're not working in silos when there is information that we can glean from each other. So thank you. And with that, I'd like to pass it off to our final speaker, Grace.
Hi, everyone. Thanks so much for being here this early in the morning. And thank you for everyone who's already spoken about the importance of plankton. I guess I don't have a transition slide. This was, so sorry. When I was asked to maybe talk about the role of zooplankton in the realm of climate change, I kind of thought of three main ideas that come to mind in how they play a role in our dynamics in our growing world. So the first thought is something that's been mentioned, and that's the biological carbon pump, and how these zooplankton play a role in not only grazing down that primary production, grazing down that phytoplankton, but repackaging them into denser pellets that can then sink to the deep ocean. And as we see changes in temperature, as we see changes in pH, we see changes in communities that may shift the ability of those. Some zooplankton are more efficient at repackaging carbon than others. And so it's always important to kind of think, what are the zooplankton doing themselves, and then who is dependent on zooplankton? So fisheries, as we're growing as a population in the United States, we've become really, and we should become more, that's an opinion, dependent in looking and sustaining fishing populations and fisheries for not only island communities, but everyone. And I think zooplankton are a trophic intermediary between that phytoplankton and fisheries management. And so one thing that's changing is as the waters are becoming warmer, we're seeing smaller, lipid, less zooplankton. And so in the colder waters, you see large copepods, you see large krill that are really nutrient rich. And then as we're seeing changes in temperature, seeing changes, lengthening of food chains, so that means less carbon, less energy being transferred up to higher food webs, and then we're just seeing food levels, and then we're seeing lipid-rich, less lipid-rich organisms. So nutrients are declining up the food web. And then, so I've talked about kind of their role in carbon export, their role in fisheries management, and then their role as climate indicators. And so the freshwater world does this really well in looking at copepods and zooplankton and different organisms as indicators of climate change, climate change and climate variability. So what we see here is phytoplankton. They look at it in freshwater and then in polluted waters, and you see shifts in communities. So this is something that, as technology is developing and we're getting better at recognizing different zooplankton and different phytoplankton, we can easily take a quick look and say these waters are polluted or these waters are not polluted. And so that gives us a good idea. Another zooplankton that I like to think is a real indicator of climate change, and we can see this is our calcifying friend, the pteropod. And so pteropods are really seen to be affected and influenced by ocean acidification as the shell structure are being dissolved due to lowering in pH. And so a lot of work is being done into using them as bioindicators and looking at their ability to kind of say, how much this population could decline over time. And as a really important trophic intermediary to fisheries, it's important to understand how these organisms can tell us what our future ecosystems can look like. So I'm honored that I was able to talk about zooplankton. We love zooplankton, so thank you so much, and thanks for listening. Yeah.
Thank you, Grace. I think your presentation and Cael's did a really nice job of bookending this session and kind of circling back on the relationship of plankton and climate change. And so I really think that was a nice way to wrap up our speaker portion. However, I would now like to welcome all of our speakers to come up to the front and have a seat so we can have a brief Q&A session. Thank you. So we have a mic up here in the front, and we will begin by taking questions from the audience if there are any. So please don't be shy. We have a microphone for you, but feel free to just shout out if you have any questions for our panelists.
Hi, thank you. It's working. Ed Hill from the National Oceanography Centre. Just combining the last talk with maybe Lynne's, you've identified plankton indicator species, and a priority of the Global Ocean Observing System is to move from the physical variables through to measurement of geochemistry through to ecological parameters. So in terms of designing a systematic part of the global observing system that's targeted around plankton, where should we prioritize those observations? Because obviously it's just a very complicated system. So yeah, how do we design a plankton observing system? Yeah.
Oh, sure. That's an amazing question. And one that I think we're trying to think about as we move ahead in zooplankton ecology, because with phytoplankton, you can see them fluoresce. And so that's an indicator that they're there. With zooplankton, it's harder to see them fluoresce. Sometimes they don't at all. I'm talking about the phytoplankton in their stomach. So I think there's been a lot of work on developing gliders and kind of gliders as observations. And I think the best place to start is in really productive regions that are dependent, that may have fisheries dependent ecosystems. And so the California Current is a great example of a place where we have zoogliders out that are taking images and pictures and reporting back and is in line with long-term ecological studies. And so we're able to kind of monitor hydrographic changes and zooplankton changes. But yeah, I think that's really imagery is where that kind of probably is going to be added, because the best way to know who's there is to actually see them. Yeah. I don't know if Lynne has an idea.
No, that's great.
Or Ken, yeah.
How much do they weigh? Yeah, whoopsie. Yeah, I was also wondering, I'm just not familiar with any, so yes, perfect. Put cameras on them, on their profiling floats and going out there. I don't have much to say. I think I just have a lot of questions.
If you have a question, you can pose it to the group. That's just fine.
I have a question about that. As we develop marine protected areas, then that also has its own distortion. If what you want to do is track what's going on in the non-protected areas to see what the stress is, and then most of our research moves over to the marine protected areas because we now have a focus there. This seems a little bit contradictory. How do we deal with that? I can't.
Does anyone want to take a stab? Okay, let's pass it.
I can take a rather preliminary step on at that. I mean, that relates to a discussion that we have also had in the context of connecting climate and biodiversity, and how to bring the discussions in the CBD together with the discussions in the climate convention. How can we actually protect biodiversity, and how do protected areas need to be set up? And as you know, the current decision is 30 to 50%, or 30% should be protected by 2030, 30 times 30. We've been saying, you know, you should be able to go up to 50 for some, it's even higher, and there should be a mosaic approach to what we call ocean, land, and seascape, and freshwaterscape. And the important thing is that this mosaic approach has corridors for species to migrate, and it's also considering that there is a spillover of biodiversity and productivity into those areas that are still being used. And I think these benefits have become visible in some places where we already have those protected areas in place. And it would be a pity if research really only focuses now on the marine protected areas without considering the spillover, because that is where there are continued human uses and possibly sustainable uses. And that's an important part of the story, because without emphasizing human interests and how they can be considered, I think our efforts to turn the curve around for biodiversity will be more difficult.
Thank you. I see there's a question in the crowd.
Hi, yes. I was a late arrival, but I watched the live stream as I was walking in, so I was able to see all the talks except for the first one. But I did want to pursue the connection between the first talk and Ken's talk around the carbon storage and the stressors and future changes in projected changes in phytoplankton population and health, particularly in the Southern Ocean and North Atlantic, where there's potential for instability in the overturning circulation.
So, Ken, do you want to? All right. So, I guess for me, it is difficult at this point to know with high accuracy or precision what the sort of future changes in carbon storage from the biological pump would be, because there are a lot of different types of processes that all play a role, and they sometimes are counterposing, and so it's a very complex thing, which is why we're continually trying to get a better handle on it. So we know it's really important, but we still struggle to understand how it works. And if you don't know how it works, you're not going to be able to say much about how it's going to change in future. I think we do have a good sense that because the Southern Ocean is a very iron-limited place, if we were to add iron there, it should have some kind of effect. But what sort of downstream effects that has on productivity other places when nutrients move around over a long time, it's all very complicated, and the ocean is very interconnected. So I guess this is something we are still trying to figure out. I don't have a good answer because I don't know if anyone does.
I was thinking when you asked that question, Julie, about one of the graphs Cael showed were model predictions of what's the magnitude of just carbon export out of the surface, and it ranged from 5 to 12 billion tons per year, the best modelers in the world. And the future changes, most of them look like they're going down, but some of them didn't. And that's just part of it. That's what's coming out of the surface. You have that whole mid-water twilight zone where the efficiency, a small change in that export efficiency, that's what's really going to change the climate dial, how much gets in the deep ocean. Because if all that carbon just gets recycled, that number could be 100. It really wouldn't matter. Or if it's in steady state, those nutrients and carbon that go down get brought back up. But as we perturb, to me, this efficiency is probably the most important number, because in nature you couldn't get kind of 99% recycling of that carbon before you get out of 1,000 meters, or during a big diatom bloom you can get half of the carbon settling down in those waters that are going to stay there. So that export efficiency, I think, doesn't get the recognition it should. And I won't say I fault paleoceanography, but the same thing. They see a sediment record and they say, oh, that's what happened in the surface. But in fact, that mid-water shift in efficiency can make a big difference on storage of carbon in the deep ocean.
Maybe one last thing to add is, I guess the way I'd summarize it is that we have a good understanding of the direction of change, but not the amount or the reason. So we are pretty sure things are going to go down, but exactly by how much or when or exactly why, that's something that I think that's part of the reason that we can keep working on this, and it's such a big problem within sort of oceanography, is because it's obviously important and it's difficult to disentangle.
Thank you. Well, we're wrapping up here. I would just like to pose a kind of a closing question to all panelists. That would be, I would like you to speak on what you think policymakers, or I should say why policymakers should care about plankton, blue carbon, ocean observing, because we are here at the COP. You know, it is a policymaker's playground. And so I'd like you to speak about what you mentioned here today and why policymakers should care about it. And we can just go down the line.
Sure. Well, so I guess I'll go back to that paper that I mentioned. I think, you know, the reason that I was excited about that result that I showed earlier is because it really demonstrates that humans are having an impact on the ocean on this tremendous global scale. And so I think it's something that, you know, when we think about human impacts of climate change, we think about heat waves or things on land, but, you know, we can now see really that we're changing the full global ocean, and it's sort of, if it's a complicated thing and it's difficult to disentangle, it's hard to know what the sort of downstream effects of that would be, or the feedbacks or the consequences. So I think that's for why it's important to keep in mind that we're having this giant global influence now.
I think just briefly why I think plankton matter and should be kind of thought of in policy is they're going to be the first ones to tell us the health of the ocean. And so they're going to respond the fastest, and then they're going to tell us what we can predict further. And so I think understanding it before it gets too far up the trophic chains or to humans, I think is really important. And I think that plankton are the things to do it, and we should really prioritize understanding them so that we can get quick responses and also improve those models so that we can get greater understanding of where the carbon is going.
Yeah, thank you. As we should all be strongly pushing for ambitious emissions reduction as a solution, short-term solution that has no alternative, we should certainly emphasize the need for ocean research and the need to improve our understanding of the functionality of ecosystems and what they are contributing long-term to climate stabilization, and under natural conditions which are changing for they're kind of semi-natural if you consider the climate shifts that are already happening. I think there is room for research, and we are far from really fully understanding the consequences of manipulating the system. And experimental studies have a dilemma in terms of only having a short-term nature, usually of a too short-term nature. Let's put it that way. So there needs to be a lot more effort before we can actually use any of the ocean large scale for climate solutions.
I guess I would simply say that, you know, plankton, they're the climate heroes. They are what make this planet livable. If you'd got rid of the biological carbon pump, you're going to add another 200 ppm of CO2 in the atmosphere. We're at 420. We don't want to be at 600, right? And so anything we do on this planet to enhance the biological carbon pump or carbon storage of the ocean is good, and that's going to involve these tiny but mighty plankton. How about that?
Yeah, I guess I'm closing up here, but I'd say that given as we move forward and hopefully are phasing out the emissions and changing the carbon exchange in the ocean, monitoring, observing, watching the spatial variability, temporal variability of the plankton and the particles and everything that are out there, the carbon exchanges is absolutely essential. And as Cael's map shows, the global scale of the trend. And if we aren't looking at that, we'll bring back to that statement. If you can't manage it if you don't measure it. And I think that's also essential as we move into MCDR. You know, talking about how to best approach regional and global scale changes in the communities.
Thank you so much. To just wrap up with some final closing remarks here. So all your presentations keenly showed, as I mentioned before, why I think it's so important for researchers and oceanographers such as yourselves to be present at meetings like the COP, where governmental and policy voices are often the loudest. As multiple of you put it so well, as Lynne just put it again, how can we expect to manage what we cannot observe, what we cannot measure? And so for both the long term and the short term, the research presented here can be pivotal for ocean climate solutions, and it must be sustained and it must be supported. And so with that, I would like to thank you all again for your presentations today, and with that, I will close the event. Thank you.